Hey guys, so today we're going to talk a little bit about determining rock ages and how that relates to the way that rocks look on the landscape. So our objectives are to define what relative age, character, the principles of stratigraphy, and apply these principles to relatively date rock strata. So the question that we're going to largely look at today is, how do geologists relatively date rocks? So far up till now in class, we've kind of been talking about how we know what the age of the earth is, and we know how old rocks are. And yes, we talked a little bit about magnetization and how we can use the iron minerals in the ocean floor to figure out how old those rocks are. But there's also other ways to figure out how old rocks are. So the process of determining how old a rock is referred to as the date or as dating. And we can date rocks in two ways. We can date them using what we call relative age dating, which is determining that one rock is older or younger than another rock, right? So the relative comes from one rock is older relative to another or younger relative to another rock, right? So in this method, we're going to be comparing two different layers of rocks. And then the other way that we can date rocks is using something called absolute age dating, which is actually assigning a number to the age. And so today we're going to focus on this relative age dating process. So first, we have to talk about the principle of uniformitarianism, which is always summed up and stated as the present is the key to the past. And so what this means is that we can understand most of Earth's rocks by comparing them to the way that rocks are forming on Earth today, right? So we can go out in the field, we understand how rocks are forming due to glaciers and rivers and in the ocean and in the bottoms of lakes and in deserts, right? We can go out and see where rocks are forming today, and we can use what we understand about how rocks form today to understand how they formed in the past, because we assume that this process has been constant and hasn't changed, right? So we sum that up by saying the present is the key to the past. All right, so let's talk about relative dating. There are a number of what we call principles of stratigraphy, and these principles, they're based on the principle of uniformitarianism, and they help us figure out which layer of rock is older or younger than another layer. And so the first one is original horizontality. The second is what we call superposition. The third is cross-cutting. The fourth is inclusion. The fifth is unconformities. So we'll talk about each one of those in turn. First principle of stratigraphy is original horizontality. And stratigraphy, I should mention, is a word for rock layers. So stratigraphy, it just means rock layers. Strata is a layer of rock. So stratigraphy is just the study of different rock layers. And we use these different principles of stratigraphy to explain and figure out what's older and what's younger. So the principle of original horizontality states that rocks are deposited horizontally. And so if you see rocks that are deformed, that are folded, that are faulted, that are not in horizontal layers, that are tilted or folded, we know that the tilting and the folding happened after they were originally deposited, right? So rocks are originally deposited horizontally, and then we could deform them later, but that deformation, the tilting, happens after they are originally deposited horizontally. This makes sense because sediments and rocks get deposited under the force of Earth's gravity, right? So it doesn't really make sense that we would make a diagonal set of layers of sedimentary rocks, right? We would make them horizontal under Earth's gravity, and then if they're tilted, that happened after they were deposited. The second principle is the principle of superposition. And the principle of superposition states that the oldest rocks are on the bottom and the youngest rocks are on the top. And this makes sense because you can't put rocks on top of non-existent air, right? So the oldest rocks are on the bottom, they were put down first, and then the next layer was put down, and then the next layer was put down, and then the next layer was put down. So sequentially, the oldest rocks are on the bottom, youngest rocks are on the top. So if we go out and we look at 4 different layers of rocks, like in a road, on the side of the road where the rocks are cropping out, we know that the youngest ones are on the top and the oldest ones are on the bottom. So go ahead, take a second, and label these rocks from oldest to youngest using that principle of superposition. You can pause the video if you need to. All right, and so the oldest rock layer is C because it's on the bottom. So using the principle of superposition, we know that C is oldest, then B was deposited, then E was deposited, then A was deposited, and then finally D was deposited last and is the youngest. So the correct answer is D. The next principle is that of cross-cutting relationships. And there's 2 ways that we can think of cross-cutting, or 2 really good examples of cross-cutting that we see in rock profile diagrams all the time. So the first type of cross-cutting is a fault. And so for example, we have our originally horizontally deposited layers, and those originally horizontally deposited layers get offset by a fault. So this fault, see how it cuts across our layers of rocks. And then the second example of cross-cutting relationship would be an igneous intrusion, right? So an intrusive igneous rock magma chamber situation. And so again, we have our originally horizontally deposited layers, and then this magma intrudes up into those layers, right? So it cuts across those layers. And so what the principle of cross-cutting states is that anything that cross-cuts the fabric is younger than the rocks that it cuts through, right? So you have to have the quote-unquote piece of paper there, right, before you cut across it with your scissors, right? So you can't cut across, it's not there. The rocks had to be there first, and then the event, the cross-cutting fault or intrusion, has to happen last. Okay, so let's take a minute and practice figuring out these from youngest to oldest, or oldest to youngest. Sometimes it helps to start from the oldest, sometimes it helps to start from the youngest. You can pause the video if you need to. All right, so our oldest layer is B. Then next is O. Next is X. Next is D. then A, and then we have two cross-cutting relationships here. We have M, which is our igneous intrusion, and we have J, which is our fault. And so after A was deposited, the next thing that was deposited was M, because it intrudes up into A, but it's cut across by this fault. See how it's offset? So that means that J is the youngest event. So from oldest to youngest, we have BOXDAMJ. All right, go ahead and try this one. I'll take a minute to pause. You can pause the video if you need more time. And the correct answer is, from oldest to younger, we have C, B, A, and then our igneous intrusion D, which cuts across all this fabric. And then E is the youngest because it cuts across not only our layers, but also our cross-cutting igneous intrusion D. Next, the principle of inclusion states that any rocks that are included in another rock are older. So a really good example of inclusion is if you have a conglomerate, right? So think of like a rock that's cemented together, one of our clastic sedimentary rocks, right? So we think of pebbles that are stuck together with mud as an example of a conglomerate or a breccia. And so those rocks that are stuck together, right, the big particles were formed before the rock that they were included in, right? These rocks were formed earlier, they eroded, got transported, right, were deposited in a muddy place where that mud got cemented together and helped form all those pebbles together into a new rock, which we call a conglomerate or a breccia, right? So think about all of the pebbles in the bottom of a river were created. And then if we turn those pebbles into a new rock, right, that new rock is younger. All the little pieces inside of it are older. Go ahead and try this one. All right, pause it if you need more time. And the correct answer is C. This one's challenging, but we know C is the oldest. Then we have A. We know A is younger than C because there are bits of C included within A. So we know these bits of C have to be older than the rock A that they are included in, right? This one's a bit confusing because A is on the bottom of the screen, but it's still only the second oldest. And then B is the youngest because it cuts across both C and A. So a really good example of this, like in a model of this in the real world, maybe you can think of making a peanut butter and jelly sandwich. And so this is something we did in school and I like loved it as a kid. So think about making a peanut butter and jelly sandwich, right? If you're making that on the counter, you have original horizontality where you put the bread down and then you put the peanut butter on and then you put the jelly on and then you put your other piece of bread on top. That would be original horizontality. And we know that we put the oldest piece of bread on the counter first, and then the peanut butter is the next oldest, and then the jelly is the next oldest, and then the youngest of all is the piece of bread that you put on top. If we wanted to get really fancy, we could inject a different kind of jelly with like a syringe into our peanut butter and jelly sandwich as an igneous intrusion. We could cut it in half, right? We could create a fault along those layers to represent those cross-cutting relationships. Or let's say, you know, sometimes when you're putting your jelly on top of your peanut butter, some of the peanut butter gets up into the jelly, right? But we know that the peanut butter is older, and even though it's included in that jelly layer, the peanut butter included in that is older than the jelly layer. All right, something important to know about relative age dating is that geologic time is continuous, right? We have a timeline of the Earth's history, and it has no gaps. But we have figured out geologic time by using all of the rocks on Earth. And in any one given place, in any sequence of rocks, there are major pieces of missing time, which we call unconformities. And this is whenever we have interruptions in rock forming processes, right? Because we're not always depositing rocks at every single location on Earth throughout Earth's history. So for example, in Indiana, Ohio, we were depositing rocks during early parts of Earth's history. And then we have a big period of missing time when the dinosaurs were alive, that rocks were not being deposited in this area, right? That's why we don't have any dinosaur fossils in this part of the US. And then we got new deposition of rocks during the last glaciation. During the Ice Age, we had new deposition of rocks, but we haven't had continual deposition of rocks in any one location on Earth. And so that missing time in a given place is called an unconformity. And there are three types of unconformities. We have disconformities, nonconformities, and angular unconformities. So disconformities are the type of unconformity where we have sedimentary rocks, we have some non-depositional layer, right? Some period where we weren't depositing rocks, and then we have sedimentary rocks on top. So these are the hardest to tell in the field because you have sedimentary rocks, some missing layer, and then sedimentary rocks again. Nonconformities are when you have metamorphic or igneous rocks, some period of missing time, and then sedimentary rocks on top. And then angular unconformities are the coolest, where we have sedimentary rocks that have been tilted, right? So we deposited them horizontally. Enough time has passed that they have been tilted somehow, usually during the mountain building process. And then after they've been tilted, we have deposited sedimentary rocks on top horizontally, right? So you have like an angular portion overlaid by horizontal rocks. So at the end of this lecture now, you should be able to answer the question, how do geologists relatively date rocks?